Let me start by clarifying a couple of things in the coursework. Firstly, what is a Cholesky decomposition? Okay, so you don't have to use it because MATLAB does it for you. But in case you wanted to do it, or wanted to know, it's a quick trick that's very common. A Cholesky decomposition is simply a way to take the square. A Cholesky decomposition in itself is the square root of a matrix. So it's a generalization of the square root of a number. So what is the square root of a number? What's the square root of 4? The square root of 4 is 2 times 2. Not 22, but 2 times 2. So what is the square root of a matrix? Well, you can write the square root of a matrix as b, well, this. Okay, so that's just a generalization of what is the square root of a number. Now, there is many, many, many ways to take the square root of a matrix. One way is a Cholesky decomposition. So we will denote the square root of matrix C. But let's imagine that we started with generating a set of uncorrelated random variables. They do not have to be mean zero. Yeah, so let's start. We imagine that we simulated a set of mean zero uncorrelated random variables. So that's the identity matrix. So we generated n random variables. So that's a vector of size n. So if you were to take that and take the affine transformation, which is x, you just define x to be a plus b, a plus, let's call it c for Cholesky, a plus c z. What is the distribution of a? The distribution of a is going to, of x is going to be normally distributed with a mean a and a variance equal to c transpose. Okay? So then if you think about it, what do I want? Well, what I really want to do is generate a set of random variables which are normally distributed with a mean mu and covariance matrix sigma. Okay, so now you can see you're done, right? Because all I have to do is say, well, let's find this C transpose, and let's find this and let's set A equals mu, and then just, if I start with uncorrelated random variables, to get these correlated random variables with mean A and covariance matrix sigma, I just have to do x equals A, well, you just choose the mean, plus the C, well, it's going to be the Cholesky of sigma times your original z's. In our context, the x was, the A was 0. We said we wanted mean 0 random variables. So if you want mean 0 correlated random variables, all you have to do is write down a sigma, do Cholesky decomposition of that sigma, that will give you a C, and then you just do C, Z. Now, you don't have to do that. MATLAB can do that for you. But if you wanted to do that, that's always nice. Of course, you cannot do this for the t-distribution, right? Because the t-distribution doesn't the variance of the t-distribution doesn't scale in an affine way because it's non-linear. Okay, so this works because the normal distribution is linear. When people say the normal distribution is linear, this is what they mean, that you can apply affine transformations of normal distributions to get new normal distributions. Okay, so just one point to clarify. Second point is, what am I asking you to do in this problem sheet? So essentially it's very simple. So I just want you to say, what is a Gaussian copula? What is a t-copula? And if we generate dependence from a Gaussian copula and a t-copula, how does this affect default probabilities? Okay, so how do you generate? So there's just 3 steps really. You either generate, what we want to start with is, we're starting with we start from a formula from the reduced form framework, which says that survival probabilities are equal to this, right? So we start with this, and then what we're going to do is we're going to simulate realized probabilities and back out what the implied default times were. Okay, so you could have said if you knew t and you knew lambda, that will give you the probability of survival beyond t. However, if you knew the probabilities of survivals beyond t, you could go the other way around and back out the t. i.e., the ti that you simulate will be equal to minus 1 over lambda I log of the probability. Now, probabilities are between, now this is the probability of a portfolio of defaults, so there's correlation, there's dependence. But one thing we know about these P's is their probabilities, so they are between 0 and 1. How many of these 0 and 1s, how many of these probabilities between 0 and 1 are we going to simulate? There's going to be n of them. There's going to be n times 1 of them because there's n times 1 assets in the portfolio that we're considering. And then the question I'm asking you is, if I generate these uniforms from a Gaussian copula versus a T copula, how do the average default probabilities look like? Right, and the answer is going to be, the answer is obvious because it's front-loaded. If we start with a Gaussian copula, there is no tail dependence, i.e. there is correlation, but there is no tail dependence between the correlation. Whereas here, there is tail dependence. And that's the big take-home of yesterday's lecture, right? So there is this slide where I show you two types of distributions, a Gaussian copula with a rho equals 0.8, okay, where it's kind of positively correlated, like this, and another type of copula distribution where there is lots of tail dependence up here, and they both have the same correlation. But correlation is not a good measure of dependence once I go from a distribution which is linear to nonlinear. That's it. Okay? Any other questions? And then to do these, the probabilities, you're just counting. You're counting and summing up. Is that all clear? It shouldn't take long. It's not meant to take long. Okay. So, today, we are going to study a commonly employed model in the literature. We're going to study the binomial model, which is commonly used to price CDOs, or a mixed binomial model. Okay, so here's the plan for today. So now we know about sensitivities and dependence. We're going to look at some contracts which are sensitive to correlation and dependence. So the plan is to look at these. We're going to sort of think about what securitization is, and then the models we're going to consider is a well-used model called the mixed binomial model, and we're going to use it to price a CDO, and then we're going to look at some more complicated models, and we're going to end up with something called the large portfolio approximation, which is due to Vazicek. All right, so we considered a bunch of individual contracts subject to credit risk, CDS, corporate bond spreads. And now what we're going to look at is what happens to contracts which are written on a basket of assets, multi-name CDS or multi-name loans. So there are a bunch of them out there. So I'd list in here just some of the famous ones. So there's a variety, a menu of multi-name products. So here are some of the famous ones, which is there is something out there called a first to default CDS basket. The first to default CDS basket is you pay a premium to insure yourself. So you pay a premium, so it's a credit default swap, so the structure is exactly the same. You pay a premium until default of the first to default within a basket, at which point the contract's finished and there is either cash or physical settlement on the single asset which defaulted, on the single loan which defaulted. So in this way, you can kind of imagine that people are insuring themselves against baskets of, within sector or within country corporate loans. There's a generalization of this, which the basket default swaps, which are the nth to default. So you cannot collect the premium. If you are the premium leg, you cannot deliver bonds until for example, the fifth bond in the basket has defaulted, or there's also a last to default version of this as well. And these are super popular. There's the iTrack indices, which are sold by Market or Mark IT. These are again portfolios where there's a basket of CDS, where each one of the CDS is valued 1/n in the basket, and so the total notion of the basket sums to 1, and the index leg pays the loss to the buyer incrementally for each one of those assets which defaults. So every time one of the assets defaults, you get 1/n of the payment of the notional. Okay, so these are written on European indices, they're written on sectors, they're super popular. You can download them for free from Market on the Mark IT website. And then something that we're going to be looking at, so we're not going to look at these today, but we're going to look at these today, and we're going to look at essentially CDO tranches. CDO tranches, which are structures which are supposed to reduce the credit risk in an overall loan portfolio. And essentially how they work is that a bunch of loans are pooled together and they're chopped up into tranches, and when any of the loans start to default within the basket or the pool, the equity tranches or the riskiest tranches take the hit first, suffer losses, up until the safest senior tranches. The senior tranches take the hit last. So the only way that the senior tranche can lose all of his money is if all of the loans default in the baskets. And these are the famous things which were sold during the crisis. And we're going to look at these a bit more. So to give you a flavour of how big this multi-name market is, here is the blue lines is the CDS space that we have looked at so far. So these are single-name CDS. Single-name CDS were massive in the early days, and so CDS, up until the financial crisis, approximately, single-name CDS were the largest proportion of the market. Nowadays, it's about 50-50. So you can see that all of the credit, this is like the credit, this is the ramp up in the credit, the size of the credit market, up until the crisis, and we've seen a decline since, but now, so this is kind of what we care about. Still, CDOs, mortgage-backed securities, are making up about 50% of the market. Okay, so what is a CDO and where did it come from? So securitization was essentially responsible for this. Securitization, I guess everybody knows or has heard of what securitization is. Securitization is the process of repackaging loans, or essentially repackaging loans by banks to sell them on to more sophisticated investors. So in principle, they're a great thing, right? Because they allow, for example, mortgage lenders who are not necessarily sophisticated investors to make loans and to pass the risks on to more sophisticated investors. So the idea being like a thrift bank or a small state bank in the US or Europe would make loans to customers who were locally based. So people making housing loans to people in Detroit So, you make lots of loans to people in Detroit, I end up with a load of risk on my balance sheet which is specific to Detroit. How do I offload that risk? Well, I can then sell it to a bank. But then the bank ends up holding a lot of risk which is idiosyncratic, and the bank doesn't want to do that. So what does the bank do? Well, what did the bank do? The banks pulled together a bunch of assets or a bunch of loans from various states or municipalities, and then they repackaged them chopped them up and repackaged them and sold them on to investors took them off their balance sheet by creating something called a special purpose vehicle, which is essentially a legal entity which takes the loans off the hands of the bank and passes them on to more sophisticated investors. So they're super clever, and they do two things. They remove the legal risk from the lender, and they pass them on to the borrower. The issue with these things is that we're going to see now is what was not very well understood about CDOs and the securitized products was what was not understood was what happens in bad states of the world because of the correlation inherent within the structures. So it was thought that the equity or the senior tranches within these structures were very safe. As we're going to see today, what is actually the correlated risk within the product actually meant that the equity was probably safer than what was thought, and the senior tranches were more risky than what was thought. So, example was the mortgage-backed security market. So the mortgage-backed security market in the end of 2008 was about 8.9 trillion, which was then three times the size of marketable debt. And this is kind of how the thing looks like. You have originators who are making loans. These are small banks in the US. And you have pooling of the loans by various originators who then sell the loans onto something called a special purpose vehicle. The special purpose vehicle is a legal entity which owns the loans and which takes the legal risk, which takes these loans off the balance sheet of the banks. These special purpose vehicles will then issue like certificates or shares, or otherwise known as asset-backed securities, to investors. The asset-backed securities are typically then categorized by various levels of risk, and the investors charge money for them, right? So there are a bunch of different types of asset-backed securities. So there's the residential mortgage-backed security market was astronomically large. So this was a very popular way of taking mortgages and selling mortgages to sophisticated investors. Also today, so this is not such a big market today. What is still a big market today is the CDO market, which is essentially the same thing, but repackages CDS and high-yield corporate debt. And then you have the CLO market, which is packaging corporate bond loans directly. All right, so that's what we're looking at today. How we're going to look at that is we're going to think about how to price a CDO with a very simple model. So it's going to be an extension of the binomial model. It's going to be an extension of the binomial tree model where we're going to allow for probabilities of up and down states or probabilities of default or not to become stochastic. So it actually turns out to be very tractable and very easy to implement. And it does give us the relevant intuition. It does give us some relevant intuition for why the market blew up. Why these structures were much riskier than people thought they were. So firstly, some definitions. Okay, so expectations are probabilities weighted by state realizations. Variances are expected squared state realizations minus the expectation of the state squared. Volatilities are square roots of variance, and so on. So, binomial model. So let's think about, we're going to first start with how to value a CLO within our CDO in a binomial model. So let's assume there are n entities that we want to think about. And the probability of default amongst any of these entities is given by a binomial distribution. So what's the binomial distribution? Well, the binomial distribution is it's a generalization of the Bernoulli distribution. So we think about many defaults being tagged together. And then the probability of a default, or probability of n defaults, will be n choose k. Okay, so this is the binomial coefficient, weighted by the binomial distribution parameter. Okay, so there is one parameter in this family, which is simply the probability of going up or down. In this case, the probability of going up or down is simply going to be default or no default on any single entity. N entities, how many probability of going to be d defaults? You just plug k into this formula. If you know p, you work out the binomial probability of default. What's the expected value? How many defaults do we expect on average? Well, the binomial distribution tells us that the mean is just n times p. And the variance of a binomial distribution, well, the variance of going up. So if you have just up or down, the variance is p times 1 minus p. And we have n of them. So this is going to be the variance of n defaults, where the probability is either p or 1 minus p. So special case is if we just have one asset, is a Bernoulli distribution. So just up or down is a Bernoulli. In which case, the probability, the mean of the distribution is p, and the variance is p 1 minus p. So when the probability of default is equal to a half, we say that the variance is maximized. So this was when the entropy of the distribution is largest, is for when the probability of default is equal to a half. Okay, we don't need this. Okay, so one important assumption about this model, which we've assumed, which we will assume a lot, is that all firms are identical. So all firms are homogeneous. So the key assumption of this model on this slide is that all firms are homogeneous, and the way that we're going to extend this binomial model and the way we're going to introduce correlation in this model is by making the p here stochastic. So we're going to assume some distribution for p. So homogeneity plus an assumption about p is going to allow us to understand some important concepts about correlation. And we're going to apply this to price CDO. It's going to be the world's simplest CDO. So I call it the world's simplest CDO because it is basically as simple as it can get, but it's very good for clarifying intuition. So the CDO that we're going to think about is going to have three tranches. Which are prioritized claims to the cash flows which come from the loans, underlying loans in the basket. The loans in our basket are all completely homogeneous. So we're going to assume that the CLO has 50 underlying loans, all homogeneous, paying a principal of 1 and maturing in 1 year, and we zero recovery default rate just for simplicity. So the tranches that we are going to consider is a senior tranche, which is the safest one, a junior tranche, and equity tranche. It's called equity because it's the most risky. So the way the CDO is going to work is that the principals are going to be equal to 35, 10, and 5 respectively. So they sum to 50, which is equal to the number of loans in the portfolio because each principal is equal to 1. So if there's no defaults, everybody gets paid off. Okay? No defaults, everybody gets paid off. If one default occurs, then the principal on equity gets reduced by 1. So the equity principal gets reduced from 5 to 4. Everybody else still gets the full principal paid off. We assume interest rates are 0 for sake of simplicity too. With 5 defaults, the principal on equity gets completely wiped out. Okay, so this is this cascade thing that you might have seen, right? That the water flows down the tranches. And it's only when it gets, the water flows out, so the water is flowing out of the equity tranche. And when 5 drops of water have fallen out of the equity tranche is wiped out. With 6 defaults, equity is wiped out, and the junior tranche, we start to draw from the junior tranche. Okay? So with 6, we lose 9, but senior is still fully paid off. With 16 defaults, which is 10 plus 5, we lose 1 from the equity tranche. Okay? So these things were set up such that there was safe stuff at the bottom and risky stuff which was meant to take the hit at the top. And so to visualize it, imagine that this is the number of defaults we have. This is what the default states look like. So with 0 defaults, everybody gets paid off. And as we run down the table, you see that the equity gets hit first, second, third, fourth. Then we're back into the junior payoff tranche getting hit. That comes all the way down. Once the junior tranche is wiped out, only then do we see defaults in the senior payoff tranche. And the question is, what is the price of equity? What is the price of the junior payoff? And what is the price of the senior payoff? Okay? The price, the 0 interest rates, so the price of the sum of these 3 must sum to the principal. Okay? All right, so what is the price of any given tranche? Well, the price of any given tranche is going to be, so we assume 0 interest rates. The price of the tranche is 6, and then the price of the tranche is simply going to be equal to its expected value. What is the expected value? So let Ti, as a function of the number of defaults, be the payoff to any given tranche, where I is equal to either equity, junior, or the senior. The expected payoff, so that's the expected payoff as a function of D, is simply going to be equal to the payoff for each level of for each default state times the probability that we obtain that number of defaults. And that index sums over 0 to the number of defaults. So for example, what is the expected payoff of equity? The expected payoff of equity is going to be the probability that there are 0 defaults times the payoff if there's 0 defaults, which is 5, plus the probability that there is 1 default times the expected payoff if there is 1 default, and then we sum that 5 times until we reach 0. After the 0, you can sum it another 50 times. You're just summing this payoff times a 0. There's a 0 times a something, right? Is that clear? So the senior payoff tranche is going to be the expected sum of all of these payoffs times the probabilities that they occur. And the question is going to be, these probabilities, how do we compute them? Okay? Because they are going to depend on whether stuff defaults altogether or not. It's going to depend on whether there is tail dependence or not. It's going to depend on whether there is correlation between the asset payoffs or not. If there is 0 correlation between the asset payoffs, what model am I going to use? If there's independence between the default states, what model would I use? It's a trick question because you've already seen it today. That's so. It says binomial distribution. The binomial distribution is assuming independence between the payoffs, in which case I can simply use this formula here in here. Okay? The point is that I'm going to introduce correlation into this model by adjusting this model. And that's going to be the point, that's the point of everything, okay? Just to highlight the independence assumption. All right, so this is what we're after. We assume zero recovery. We could just plug in the binomial probabilities if we had independence, but what we want to do is take into account that there is dependence between the default states. All right, so a quick trick to compute under the assumption that there is, let's start with the assumption that there is independence, okay? So punchline is, it's going to be unlikely that they ask you to derive or to implement the mixed binomial model within the exam, because that would take a computer. However, it's even quite tricky to implement the binomial model within an exam because your calculator is not going to have enough digits on it to compute the binomial formula for large numbers unless you use a trick. So, if you try to, let's say we have 100 assets, for example. Suppose you have a portfolio independent of defaults. Suppose you have a portfolio of 100 assets. And I tell you the probability of default of any given asset is 6%. What is the probability of observing 5 defaults, assuming the binomial model works? Well, if you were to try and compute this number here, which is the binomial formula, your calculator will not be happy with you. If your calculator can compute this in the exam, it's not a legal calculator. So what do you do? Well, because I want to compute, for example, this number here, which is the probability. Let's imagine we have 100 assets that n is equal to 100. So this is going to be 100 factorial times 6 minus 94 factorial. That's an enormous number if you try and do it on its own. The trick here is that there is also another version of the binomial coefficient, which is this one, which is the one that you can compute by backward induction. So this number here is identical to this, which is a nice, easy exercise, but nice exercise to show. And how would I then compute this number here, which is if I had 100 assets and there is a 6% default probability, what's the probability of well, here I'm computing the probability of 1, 2, 3, 4, 5, 6. So not 5, I'm computing the probability of 6 defaults here. You plug this in, 100 times 99 times 98 times 97 times 96, all the way down to 95 because there are 6 defaults. And then you normalize by 6 factorial on the numerator and then plug in the probabilities. And if you do that, I think you get a probability of observing 6 defaults equal to 16.5%. Okay? So in principle, if I gave you the equity tranche, you could use the binomial formula to compute this binomial formula to compute the expected payoff to the equity tranche, right? Because you just need to compute the probability that there are 5 defaults, 4 defaults, 3 defaults, 2 defaults, 1 default, and then use this formula here. All right. Okay, but now we're going to generalize things a little bit. We're going to introduce something called the mixed binomial model. Well, you compute, if you wanted to do equity, you need to compute the probability that there is a non-zero, the probabilities that you just have non-zero payoffs. Right, because where I wrote this formula here, that index potentially runs from 0 to 50, but only for the senior tranche. The equity payoff, the equity payoff has 1, 2, 3, 4, 5 non-zero entries. So you would compute the probability there are 0 payoffs, 0 defaults, multiply it by 5. Compute the probability there's 1 payoff, multiply it by 4. So you're going to compute 1, 2, 3, 4, 5 probabilities. Because everything else is obviously multiplied by a 0. So. Okay? All right, cool. So here we go. So what we're going to do now is something interesting. We're going to adjust this model for in a relatively tractable way, and it's going to introduce correlation. So we're going to go from a binomial model to a mixed binomial model. And the intuition here is that we're going to make the mixing parameter, so the p, so this p in the binomial formula is otherwise known as the mixing parameter. So because you're mixing p1 minus p. And we're going to think about that p as being a function of the state of the economy. We're going to think about probabilities of default all going up in recessions. Or they're going to be a draw from a right-hand tail where all the probabilities go up. And that's going to introduce correlation. So we're going to make the p stochastic by giving it a density. We're going to assume it has a density f. So our p is going to become a p tilde. And we're going to introduce that p tilde into the binomial distribution. So the generalization looks like this. Is this thing here. So everything we're going to be working with today is related to this. Let's take a look at it quickly. So again, it's like, what's the probability of observing d, assuming p is a random variable itself, which has some density f. What's the probability of observing d defaults, or k defaults, sorry? Well, it's the probability, it's just the binomial probability here, integrated across all of the possible p's. Okay, so it's this binomial probability integrated against its density across all possible p's. But of course, probabilities are between 0 and 1, so we just have to integrate between 0 and 1. So integrate this against its density between 0 and 1. And then the question is going to be, what is the density of p that we pick that's going to make this tractable? I mean, there's going to have to be two issues here. One, we're going to have to pick a density which is bounded between 0 and 1. There are not many of them. There are very few. And we're going to have to pick not only a density which is bounded between 0 and 1, but we are going to have to pick a tractable one. So tell me which density I'm going to pick, which either tells me that someone already read the slides or someone is smart. No, because it's not going to be tractable. Well, that wouldn't be a density that's bounded between 0 and 1. That would be, I can take a logit of another distribution. We're going to use a beta between 0 and 1. So that's a distribution bounded between 0 and 1. And it's always used in probability like this. And it turns out it's super tractable. The beta distribution is just a generalization of the binomial factor. All right, so where we're going to go with this is f is going to become a beta distribution. The distribution of p is going to be a beta. To give you an example of what this would look like, imagine that we could have, however, picked, so the beta distribution is going to be a generalization of a binomial, or, yeah, it is going to be a generalization of a binomial. So there are three distributions we could have picked. One is a beta, one is a binomial, which is this. So we could have assumed that the probability either takes a high or a low state, which is either P1 or P2, with a probability f of P1 and a probability f of P2. Because this would have just been a discrete switching state. Okay? So this is the idea of what we're going, and we want to think about this in a continuum. The way we're going to think about this in a continuum is we're going to pick B to be, or F to be beta. All right, so we're going to need to know this. So this, at the moment, is one of my favorite formulas for reasons I won't explain. But what is the conditioning state? So how can we condition down? What is conditioning down? So this is something called the law of iterated expectations. So this is the law, and this is the law of total variance. And in general, they are both something about, they are something called conditioning down. What they say is that the unconditional, so this expression here says that the unconditional expectation of a random variable is simply equal to the expectation of the conditional expectation of that random variable conditional on y. The law of iterated expectations does make sure that probabilities sum up to 1. The variance version of the law of iterated expectations is the law of total variance, which says that the expectation of a conditional variance, so the unconditional expectation variance of a random variable, is equal to its expected conditional variance plus the variance of its expectation. Right? So these are just two results that we're going to use in the next couple of slides. And what we're going to use these with is we're going to assume that x is the random variable that we care about is d, the number of defaults, and the y we're going to condition on is p. So we're going to want to think about statements like, what is the expected number of defaults conditional on p, or what is the variance of the number of defaults conditional on p, where p is going to be something drawn from a distribution and it's going to change around over time. Okay, so let's think about the simplest case of this model, where there's just going to be one entity. And if there's just one entity, so there's just one entity, and we're going to call them xi. And there's going to be, x is going to take on a value of 1 if there is a default and 0 otherwise. Okay, so it's 1 if there's a default and 0 otherwise. So it's going to be p times 1, 1 minus p times 0. So p is going to be, okay, so that would be the expected number of defaults. So p bar, we're going to denote as the mean of this random p variable. What's the expected number of defaults? Well, to compute the expected number of defaults, we're going to use this conditioning formula from above, the law of iterated expectations. It's going to be the expected number of defaults conditional on a p bar, and then we take that expectation. What is this? What is that number in the parenthesis, inside the wider parenthesis? The expected number of x conditional on p bar, so p tilde, is just equal to p tilde. Right? Conditional on having a, if I knew what p tilde was today, what's the expected value of x? It's just p tilde times x plus 1 minus p tilde times, sorry, p tilde times 1, because it takes on a 1 if there's a default, plus 1 minus p tilde times a 0. So this stuff in the middle here is just equal to p tilde, and then the expected number of defaults, the unconditional number of defaults then, is just the expected value of p tilde, which is just the average p. Okay? So the expected number of defaults is just the average p. So that's nice. You can also, if you go through that exercise which I just did, so you know that bit there. So that bit there is just equal to, that bit there is equal to that bit there. So it's equal to p star, p tilde, and then you have to take the expectations, and if you do the algebra, you can see that you end up with the variance of the number of defaults is just p bar 1 minus p bar, which generalizes just the Bernoulli result. Right? It just generalizes that result there, that the variance of a Bernoulli distribution is p 1 minus p. So it turns out with a mixed binomial formula, it's still nice. It's just equal to p bar 1 minus p. You just need to know the mean of p. You can also show that the covariance between the default on any two entities is equal to this animal here. Okay, the expected value of p bar squared, or p tilde squared, minus p bar squared. So, now you can see something that, what we think, this is what we're interested in. So this animal here is the covariance between defaults. So now we can see that actually this is a non-zero number. Right? This number is going to be non-zero. There's going to be now covariance between defaults just because we made p stochastic. The intuition being if there's independence between default, if we have a binomial distribution, there's independence between defaults. But you can think about this as being, well, suddenly we're in a recession and the probabilities have all gone up. We've drawn from a right-hand tail and everything's more likely to default. If everything goes from less likely to default to more likely to default, the correlation between defaults is time varying. And that's why we end up with a non-zero covariance. And you can see that this is actually zero if you make p-bar constant. So if we go back to the binomial world, that p-bar would be constant. So it would just be a p-bar squared minus p-bar squared, and there'd be a zero covariance between defaults. And you know, this would be also, I guess, a simple question I could ask you in an exam. All right. Something which is less easy to understand is the correlation. The correlation is simply the covariance divided by the variance. It's a bit of a messy number to interpret, but you know, that's why we just think about stuff in terms of the numerator. Okay. All right, so before I move, okay, so what we're going to do next, so this was one asset, or this was just thinking about what happens with one asset. Now we're going to move on to thinking about what happens with two assets, but I don't want to go too fast, so let's take a break and let our brains rest or ask questions. Yeah.
Because I read the step and then non-linear correlation.
Yeah, so the correlation will be linear when I have a Gaussian copula.
Yeah, but then before the transformation.
So that's, yes, but then after the transformation, the correlation. Yes, let's say we have, let's start with a Gaussian. We generate uniforms, yeah?
Yeah.
So a Gaussian with a rho equals 0.8.
Okay.
We generate uniforms. Okay?
Mm-hmm.
They will be uniforms, but they will have a correlation of 0.8. So if you plotted them on a, if you called one of them U1 and one of them U2, they would be positively correlated like this. Okay, but they would have no non-linearity. There wouldn't be any like additional mass here. There wouldn't be additional mass here.
So non-tail.
There would be no tail dependence. Let's do the same exercise, but now we generate a T copula with exactly the same correlation. Exactly the same. We do generate the uniforms, and then we plot the U1 and the U2. If you compute the correlation between these two, you'll get, if you compute the linear correlation between these two, you will get 0.8 roughly by a simulation. If you compute the linear correlation between these two, you get 0.8. But if you plot them and look at them, okay, there will be a positive correlation. There will be much more in the tail and much more in the tail pin.
So, okay,
So the copula part is when we go from, you know, the copula says that we can have any distribution, a cumulative distribution function of some marginals. Right, so F1, F2. So the copula is that we generate some, from some set of marginals, we generate these. So you're doing this bit. You know, you're inverting. You're taking a Gaussian. And you're generating some uniforms. So you're pulling out these marginals. The F is this.
okay.
The F is this.
Okay.
And then by a particular copula to get a uniform.
So from this we have the uniform.
Yes, yeah, that's right. And just the point of the exercise is, look, I can take these two different copulas, one which is linear, one which is non-linear, in the sense it has fat tails, and I will get, with the same correlation parameter, I will get very different probabilities of the fall.
Okay, so for example, if I have two, because in the example yesterday you generate like two identical distribution columns.
Yeah.
So what if the distribution of the two columns is different?
You could do that as well.
So I would do the same thing, like I could invert
Yeah.
to copy uniform.
Yeah.
And then, yeah, so I understand up to this part, and then but what after that? What is it after?
Well, there's many things you can do with it, but what we're doing in this exercise is one particular thing, which is, look, just to say, if I get these uniforms, I can use these uniforms to back out, simulate default probabilities. In the example I was giving you, I was saying, look, let's generate, in my example code, I generated a Gaussian, I transformed it to the uniforms, and then I transformed it again to two different ones, to a beta and a T.
So and then compare, because the thing is that
But then my beta and my T would have had, still had a correlation of 0.8.
oh, so the correlation is
The correlation is the important part. The copula is the correlation. The copula is the thing which it separates the marginal distributions, allows you to separate creating distributions from having a correlation between the distributions.
so the correlation would still stay the same, but
Yes.
then I can transform it to another distribution.
Yeah.
That's at design.
Yeah, so it's basically a way of transforming stuff to different distributions as you like, while still maintaining the same correlation.
Okay, so for example, if I have like a bond price, two bond price,
Yep.
and then I estimate the correlation between the two,
Yep.
but then maybe the distribution is different. So I still can like get the correlation between the original and the original.
Yeah.
But then how do I transform it to uniform since, because maybe I don't know the distribution yet, so how do I transform those to
Imagine you knew the okay. Imagine you knew the distribution. Let me be a good example. I mean, imagine that you knew the distribution between, you knew the correlate. You wanted to think about the correlation between stocks and bonds. That would be a better example, because maybe stocks have got a more heavy tail. We know the correlation between stocks and bonds. Let's say it's 50%, but we think stocks have more heavy tails because there's more jumps, whereas bonds are more they're more Gaussian. So we could start by generating a Gaussian distribution with a correlation of 0.8. Then we would convert it to uniforms, and then from those uniforms I could pump it into a T distribution versus another Gaussian distribution. And these could now represent the distribution of my stock returns versus the distribution of my bond returns. Now I have two different distributions for stocks and bonds, but they have the same correlation I could have estimated in the first place.
and then I can use those distributions
Then you could say, let's try to price derivatives based on
this.
these two distributions. Right? So then you pull out many numbers from here, many numbers from here. I could price a derivative. And you could also price a derivative on the two. Right? If I pull out many observations from one, many observations from another, right? And then I could price a basket option on those derivatives.
The first thing I have to assume the distribution each.
Yeah, exactly. Yeah. But you can estimate the correlation.
Yeah, so like I can from that level, I can.
Yeah, I mean, you know that you can also do something like, look, what is the historical distribution of stock returns? It looks like this. What's the, right, and it will maybe have a very, well, probably not like this, right? Fat left tail. Now what's the historical, let's say we model this as a gamma, or, I mean, this could be log normal something, or it could be a skewed T distribution. You do the same things for stocks, but it's like this, so you say, okay, it's normal. So, but you compute the correlation and it's equals to 0.5.
So generate a Gaussian, transform that Gaussian to uniforms.
And then
Transform that to T, this one to Gaussian, and then draw many different realizations from the two and price an option on the two, a basket option. That's the sort of thing people do.
Okay, so let's move on now. So what we just did was the case of a single issuer, and we ended up with these results. Now let's do the interesting case where we have n borrowers. Again, D is the number of defaults. It follows straight away that since everybody's identical, the number of defaults in a basket of n assets when there's a stochastic P is just n times P bar, which follows just from this result here. Okay, so if there was an n in front of this, we would just pull the n out, and we'd have an n P bar. Variance, you can compute in a similar way. So this is the variance of any individual default. So, okay, so here is the variance. This is conditioning down again, right? So this is the unconditional variance of default is equal to the expected value of the conditional variance plus the variance of the expected value. So this is the variance of the expected default, and this is the unconditional, the expected value of the variance. So the expected value of the variance is equal to this term here. And this, you'll notice, is exactly the same as this term here. So it's like the covariance term. Okay, so it's like the covariance between any two individual defaults. How many of them are there? Well, we don't want to avoid double counting, so there's n minus 1. Okay, so how many elements in a matrix? n minus 1 over 2. This is how many times we count. Okay, so what you can see here now is that we have two terms. If there is zero, so this term is the variance of this term here is variance of P bar, P tilde, or the variance of the mixing parameter. What you can see here is if this doesn't have any variation, if the P is a constant, we're simply back to the binomial world. Okay? So in this case, there is zero covariance. There's zero covariance between the shocks. That's simply when the P is constant. There's another extreme. So the covariance term is a little bit hard to interpret here, and so I just give you some intuition about how P relates to covariance. The idea here being is if the zero, if P is flat, if it's not varying, there's no covariance between the defaults. In another extreme, there is a lot of covariance. What is the other extreme? The other extreme is when, imagine that P bar takes a value of 1. So P tilde takes a value of 1 with a probability P bar. So it can just take two values. It can either be 1, so everybody's defaulting with probability 1, and that happens with a probability P bar, or 0 otherwise. If you plug that into this, you end up with this result here, which says that when there is a very lot of, so even in the case where there's perfect correlation between defaults, so this is perfect correlation, we end up with this result here. Okay, so these are the two extremes, where we end up with a zero correlation, the variance is equal to P bar 1 minus P bar, and if there is perfect correlation, that is n squared times larger. Right? So going from here, if there's no variation in P, I end up with just this term, whereas if there is perfect correlation between the asset defaults, which happens with the probability P bar, I end up with this result. And this is the key insight to the model. That the higher the variability, so if P can only take on two values, the highest variability it can take is if it takes on P takes on a probability 1 or 0, okay, with probability P bar. So this is the key insight here, that the more P moves around, the larger is the correlation between the default events, and the larger is the variance of the number of defaults. Okay? So not only are they more correlated, but they're more variable. Actually, you can say one more thing. So here we've actually got close to deriving a version of the law of large numbers. Okay? Which is that if we think about the loss fraction, which is what is the variance of the number of firms that default as a fraction of the number of firms that we have. Okay, so to compute this, you just divide this result here by n. Just divide an n in here. So I'm going to end up with an n squared here and an n squared here. I should have had an n squared here, I guess. Yeah, so I should have had an n squared here. And then if you work out the algebra here, you'll see that this goes to this number here. This number here, or this object here, for very large n, this goes to this number here. So when there is a very large number of assets in the portfolio, the variance of the loss fraction, what fraction of defaults do we expect? The fraction of defaults goes to this object here, which is the thing which keeps popping up. It's the correlation, it's the covariance term. Okay, so the variance of the loss fraction goes to the covariance term. Actually, every moment of the distribution in this model goes to this number for a very large n. So this is kind of like a cool result because it's similar. It's a law of large numbers result. The law of large numbers says that if I draw very, very many times, then the mean of the distribution goes to a normal. The mean of a distribution will be normally distributed. This is like saying that if I draw very, very many large numbers, everything goes to this number. Okay. All right. So this is the general setup, right? So these are the general equations, and now it's like come down to, well, what do we pick for this distribution? We want to pick something which is analytical. So we've already established that one of the analytical things that we pick is going to be a distribution whose support lives on 0, 1, and it needs to be analytical. And it turns out that the beta distribution is an analytical object that we can pick for p bar. So there's two sides to this. A, it's going to turn out to give us a closed form solution to this model. So you can do this in MATLAB in a loop pretty quickly. In fact, I've posted the solution to the code that computes the pricing of the CDO is on the hub. So it's simple in a statistical analytical sense, and unfortunately, but it does not have any real economic intuition. So we have no economic motivation for picking the beta distribution, and that's why after this we're going to look at some sort of more economically motivated way of studying default within CLOs. But you can kind of motivate it. There's this interesting fact that, I mean, if you go to Wikipedia, it'll tell you what is the beta distribution. Well, the beta distribution is something which arises from selecting an urn. So, okay, so if I was to take an urn with alpha red balls and beta black balls, and every time I picked a ball out, I simply replaced that ball. After doing that n times, what's the probability that I pick an alpha? What's the probability that I pick a red ball? Well, that follows a binomial distribution, where the binomial parameter, where the mixing parameter is simply the fraction of red balls in the urn. So if I know the fraction of red balls in the urn, and I do this game where I pick a ball out and I put it back in, I pick a ball out and I put it back in, and I repeat that many, many times, eventually that becomes, the probability of picking a red ball becomes a binomial distribution. The beta distribution is closely related to the binomial distribution, and this is why it works. Well, this is why it analytically works. If I pick that ball out, the red ball out, and I get a red ball, and I put 2 red balls back in, and then I pick a black ball out, but then I put 2 black balls in, and every time I pick a ball out, I put a ball back in, and then if I know what the fraction of red balls is versus black balls, alpha versus beta, the distribution is going to be a beta distribution. The difference is with replacement, simple replacement versus, what do you call it when it's non-simple replacement? Repeated replacement. Okay, so they're closely related in a statistical sense. And just if you do that same game without replacement, so if I pick a red ball and then I compute the fractions of red versus black, and then I do that many, many times, if I do that game, then that distribution turns out to be a hypergeometric distribution. So these are closely related distributions, and this is why it works. Now, if you're thinking about if you think about what this means in our context, it's like every time you observe a default, you put 2 more defaults back in. And we play this game many, many, many times, then what is the distribution of defaults? Okay? So this is why this model sort of lacks any economic intuition, because that game of taking a ball out and replacing 2 does not easily translate, at least in my head, to what replacing 2 defaults means. However, it's analytical, and this is what it looks like. So it looks like the binomial distribution, except now it has 2 parameters because of this replacement game. The binomial distribution, if you remember, is only going to have 1 parameter, k and 1 minus k. So the binomial distribution only has a mixing parameter and k. Now we have an alpha and a beta. So this is like the idea of the balls moving around. So it has 2 parameters, and the density function is beta. It's a function of 2 parameters, alpha, beta, and a certain probability. So this bit here just looks like the binomial distribution. But now, instead of having the binomial parameter, or the binomial coefficient here, we have this function here, which is a beta function. And the beta function is just a function of 2 parameters. And it ensures that when you integrate this, it sums to 1. That's all that is there. It's a constant of proportionality. So this is just what the distribution looks like. It's analytical, so we can compute what the expected value of P is. Okay? So you can invert this thing, and you can compute what the expected value. So this is what we're going to choose for the this is the distribution of P. So this is going to be our F of P. Okay? This sums to 1 once you integrate it with respect to if you integrate this between P equals 0 and 1. Okay? If you integrate this with respect to P equals 0 and 1, for any given alpha and beta combination, it will integrate to 1. So that's why it's a valid distribution function. You can compute the expected value of P by doing P, F of P, dP. That's analytical, and the mean is going to be alpha plus beta, the fraction of alpha over alpha plus beta. That's not that important. What is important, that is important. That's going to be important for our calibration. So we're going to calibrate, you can calibrate the model to any particular P by picking different alphas. But you can pick, what's going to be interesting about this is that you can pick imagine we pick a P, which is alpha is equal to 1 and 9. Okay, if I picked an alpha equal to 1 and 9, I would have an expected P tilde of 1 over 10, so it would be 0.1. Expected P would be 0.1. If I now look at the variance of this, I could also have done, let's pick an alpha of 10 and 90. I'd have also got the same P, right? I'd have got 10 over 100, I'd have got 0.1. The interesting thing about this distribution is that for any given set of combination of parameters that produce the same P bar, which is the mean here, then the variance will fall when alpha increases. So for a given P bar, the variance is decreasing in alpha. The variance is decreasing in alpha, which means that if I go from a P bar where if I go from P bars 0.1 because it's equal to 10 over 100, so 10 over 10 plus 90, that gives me a p bar of 0.1, and I go down to the same p bar, which is going to be 1 over 1 plus 9. It gives me the same p bar, but the variance of the second one is going to be larger. So when alpha falls for a given p bar, the variance goes up. Okay? That's going to be important, right? Because the variance of p bar is closely related to the correlation. Because the variance of p bar, the more variable is p bar, the more variable is the number of defaults. The more variable is the number of defaults, the larger is the correlation between the defaults. Okay, so these kind of are parameters that you can calibrate in your head. Okay? Okay, and now the magic. And it's just a couple of simple steps. So this was our distribution. Let me just walk you through these steps. So this animal here was what we started with. We wanted to generalize the binomial model to the case that P was stochastic. So we wanted to pick a density for P. And then what is the probability of having K defaults? Well, it's the binomial parameter integrated, it's the binomial distribution integrated across all possible combinations of the mixing parameter, which obviously is between 0 and 1. So let's substitute in this F to here. Okay, so this is a constant, so we can bring these two things out. And then what you end up is a nonlinear combination of the alphas, but you end up with a product of lots of p exponentials or p exponents. So if you just take a look at this, I can group the p's together. What do I get? I get k plus alpha minus 1. That's this one. I can group the 1 minus p's together because this is coming from. Sorry, this is coming from here. This is coming from here. This was the original p 1 minus p's. So I end up with this 1 minus p n minus k here. Is this 1 minus, so this is n minus k plus beta minus 1. That's that number there. Okay, so then the only trick is everything is outside, and I need to integrate that between 0 and 1. But if you look at this and imagine taking the beta coefficient to the other side, well, if you imagine looking at this and integrating this, if you integrate this between 0 and 1, it integrates to 1 because it's a density, right? So then you just need to make the observation that this here is like replacing the alpha minus 1 with k plus alpha minus 1. Sorry, this alpha minus 1 is like replacing the k plus alpha minus 1. So it's just like adding a k to the alpha here. Here, this is beta minus 1. So this is like adding an n minus k to the beta in here. And then because the density sums to 1, you can imagine bringing this outside. So this then just simply comes up, and the integral disappears. Okay? The integral is just equal to 1. Okay? So there is our analytical result. So the probability of observing this number of defaults is just given by this number, which is a product of the binomial coefficient and this additional beta function normalized by this number, which just makes sure the distribution sums to 1. So I posted, this is online, so you can play about with this. And now we can see exactly how the alpha, now the point is, we've made the world stochastic. We know what, for a particular p, if we lower alpha, the variance goes up. So we can see how we can finally price our CDO. Okay, just to remind you how we're pricing our CDO, it's just this formula here. Okay, so we have just computed a closed form solution for this P, where we have a stochastic mixing parameter, and we just need to take the product of that thing with the principal on each at each payment point. For each principal with the probability, and sum them all up. Okay, and so here is the results. Okay. Okay, so what is the price of equity? What is the price of the junior, and what is the price of the senior tranche? So, here, everything I'm choosing to have a probability of default, the average probability of default, equal to 0.1, 10% for every single loan in the portfolio. For the binomials, obviously constant, and there's no correlation. Okay, so this would be like an exam question as well. Here I have the beta mixture distribution, where I have an alpha and beta of 10 and 90. So again, I have a average P of 0.1, and here I have a mixing parameters of, so the beta parameters of 1 and 9, and so again, it's just equal to 0.1. And now my question is, if you take a look at these results, you'll see what happens when you go from independence to the variance goes up when the alpha falls for a given P. So this one has the largest correlation, and so this beta model has a larger variance and larger correlation than this beta model, because for a given P, if we lower alpha, the variance goes up. Okay? All right, so now what? So if you take a look at these numbers, and if you stare at this question for a couple of minutes, can tell me what happens, and tell me, is it surprising? The point of this also is that maybe pre-crisis we didn't really understand the effects of correlation and the effects for these complicated objects. So we thought senior was very safe, and maybe it was less safe than we thought. So feel free just to tell me what's happening at any point in time. So as you increase the correlation, what happens to, let's focus on equity versus senior. Yeah. Okay, so that's the first part. So it is unexpected. And what's the answer? Why does that happen? Feel free to talk. Yeah, that's quite close to the answer. The first part's correct. So the idea here is that when you increase correlation, so the point that your colleagues are making over here is when I go from senior, so forget about junior. I mean, also for junior, the effect is interesting, right? So for senior and junior, what happens is as I increase the correlation of defaults and thus the variance, or the variance and thus the correlation, the expected payoff actually goes down. I mean, the numbers aren't massive, but we could have picked different numbers. What's important is the direction it goes. And also the same is true for the senior, but the equity actually goes in the other direction. Right? So what is surprising here is the directions that it go in. But actually, the reason that it happens is the reason the equity and the reason that this happens is because of the two. There is the effect of changing correlation is the following. So these are the two beta distributions corresponding to this and this. This is what the distributions look like. These are distributions that sum to 1. They're distributions. So they have the same mean, which is the mean of it's this p bar, but they have different variances. The so as alpha goes down, the variance, and thus the correlation of defaults, goes up. But if you fix the mean of something and you increase the variance, there is two things that happen, right? So there's essentially you increase the variance on one side of the mean. So fixing the mean and increasing the variance, you must increase the variance on both sides of the distribution, the tails on both sides of the distribution. So this one looks relatively normally distributed, right? Or it looks symmetric. Fixing the mean and spreading the variance, I introduce fat tails on this side. Okay, so this is the mixing parameter. It's between 0 and 1 on the x-axis. So I increase the probability of a large number of defaults, but I also increase the probability of a small number of defaults too. Right, there is more mass there is more mass here, and there is more mass here. Right, so for a particular mean, that's what must happen. And that's why you end up with this situation where increasing the variance, thus the correlation, actually increases equity, because actually now there's a fewer chance of low number of defaults, and the senior and junior tranches actually decrease because, as your colleague says, what can actually hurt you here, the only way equity can get hurt is if there is a very large number of defaults. But the consequence of increasing correlation, i.e. everything gets bad or everything is good, is that both of these two things go in a different direction. And that's like a kind of nice lesson for the crisis period because, well, I guess people knew this, but you can imagine things can get more extreme and more complicated, but the intuition about the different tranches not being as risky or as safe as you thought is coming from here, right? That there's this time-varying correlation in crisis periods. All right. What's the time? Okay, so let's take another 5-minute break, and then we're going to actually think now about, so this is unsatisfactory in a way, right? Because what I said about the beta distribution is, what does it mean? It's picking the alpha, picking from an urn, and with replacement. But it doesn't mean too much in the context of default. So actually what we actually want to do, what you could do is you could pick the alpha and the beta to match the data, so to speak. And you could use this as a default indicator. But what we're going to do now is actually we're going to extend the Merton model to include a stochastic correlation parameter. And this is going to be called Vazicek's model, but it's going to take us an hour, so let's take one more 5-minute break. Can you? Let me take that thing off.
Well, I mean, that's in the background, right? So we're using this if you have a look at the extreme, yeah, so the extreme cases, we have, rate times lambda, right? We're trying to estimate these S's for, trying to estimate, we observe these S's, and then we're trying to back out these lambdas for lots of different maturity values. Imagine that now, are you going to back out here? Story doesn't work for R equals 1. Yeah. Because now we're going but actually for some R, if R is not, if R is too small. I mean, we cannot necessarily know that they're positively or negatively related, actually. The whole thing is some non-linear. With just this simple, that you could have done, you could do it maturity by maturity. Actually get something. Not necessarily have you, that you're going to obtain a. But what is true is that when this gets close to 1, but it depends if you have no, if you go to R equals 0, then the full probability should increase. If you pick, for example, if you put R equals 1 and try to solve this, try to figure it out. realization. That is the same as that term here. Yeah, the same term. Now we need to compute the variance of the expected value of P. What's the expected value of P? This is the variance of this term here. Variance of this, it's the variance, yes, and D is it says the variance of value of expected value of D bar is this term here. Okay, but it's the variance of this term. The variance of the MD bar is n minus 1 because we don't want to double down. So this would be like n squared. We don't want to double count, so we minus 1. And then the variance of P tilde. Yes, exactly. Yeah. That's the variance of P tilde.
So this is equals to variance of P tilde.
Yeah, that's just the variance of P tilde.
Variance.
Because this x is either equal to a 1 or a 0. What's the variance of x given P tilde? Or 1 minus P. Variance of this x is just no, I would give you like there would be clues no nothing is going to be memory.
The difference between these two.
Yes. And this, yeah. So the previous page it was just applied to the one asset case.
So that is applying to.
Okay, so just a quick clarifying question about what you should and shouldn't know for the exam, since that's getting close. I'm sure those questions are coming. It's definitely not a memory exam, so it's not going to be, I'm not going to ask you to state this. I'm not going to ask you to state anything, but you will have to remember things which you should know, like the Black-Scholes formula. You should know that. You should be able to tell your grandmother about that. And what are the beautiful things about it. Remember the drift disappearing, that stuff like that. And the link between the drift disappearing and risk-neutral pricing. These are important things for your life in general. And this kind of, you know, and you should also know the binomial formula. And you should know how to apply the binomial formula to a simple thing. You should know what a CELO is. You should know how to compute things like that. In-depth derivations won't be on the exam. Okay? All right. And I will try to clarify a bit more next week. What are the style of exam questions you can expect? All right. So this is the binomial model is a nice model for clarifying intuition and statistical intuition. For example, how does correlation and variance affect the pricing of basket options or multi-name credit derivatives? But it lacks intuition. And so what we're going to finish with now is a more intuitive model which generates dependent defaults. It's going to be an extension of the Merton model. So I guess to motivate, again, a little bit why we want to think about defaults being dependent. Here I'm showing you something from Standard & Poor's which shows you the number of defaults in investment grade versus speculative grade debt. So again, another exam thing, you should know that defaults are correlated in bad times. Why do we want to think about, why should we think about models in which default correlation is time varying? Why should we think about that? Because that's the way it looks in the data. In the data, there are cycles of defaults. So this 1990, 1991, that's a recession. 2000, 2001, 2002, that's a recession. That's the 1990, 1991 recession. That's the 2000 dot-com bubble recession. And everyone knows that that's a recession, right? So they tend to be spiking recessions, and even more so for speculative grade debt than investment grade debt. And so we need models to account for that. The simple one that we're going to consider now is the model that we all really love and know off by heart, which is the Merton model. So this is an extension of the Merton model. So Vazicek did, well, Merton owes a lot to Vazicek. So as far as I'm aware, Vazicek is the richest finance academic to ever have lived. And he got his wealth by attending Merton lectures. And he did two things. I'm showing you the second one. So I don't even know if I told you this story, but I met him once at a conference where he was giving a keynote speech. And he's quite an old guy now. And he was wearing a full-on, he's from Serbia or Czechoslovakia originally. Anyway, he was wearing a full-on cowboy suit with a cowboy hat. And he had a remarkably good-looking 21-year-old girlfriend. But other than that, so he did a lot of things in finance. So the Vazicek model, which was an application of him learning PDE theory from Merton. What was the other thing that he learned? That he gained from Merton, which we've already studied? The K, the M, the V. He's the K. KMV Merton, the KMV Moody's that was sold to Moody's for lots of money. That's why he has his money. He's the Vazicek, he's the V in KMV. And he also came up with this model here, which is the Vazicek correlated. This is like the industry standard for thinking about how we should think about correlated defaults. So this is a paper in the JF from the late 90s. It's actually relatively simple, and it's using the idea of, it's using a simple idea here. So we're going to take the standard Merton model, where we're going to have lots of firms, and A firm, again, is going to default when the value of the assets fall below a threshold at some maturity T. And we're going to note the value of the ith obliger VI-T. We're going to assume that VI is normally distributed, and we're going to normalize VI. So you can do this in a geometric Brownian motion sense. Just for clarity here, we're going to normalize everything because it does make the algebra quicker. Let's assume that every asset at date T has a value of 0 without loss of generality, right? Because we only care about whether it goes up or down, really. So you can add a constant to this, it doesn't matter. And we're going to assume that the value of the asset is, so initial value of the assets are equal to 0. This should probably say Vt plus 1 or T plus delta. Doesn't necessarily matter. Is normally distributed with the mean 0 and variance 1. So we've subtracted the drift, and we've got rid of the volatility. So you can think about this as being, this is just the Merton geometric Brownian motion, but with a mu equal to 0 and a sigma equal to 1. I've just normalized it, right? So that's just going to remove a bunch of mu's from everything and sigmas. It's going to make the algebra easier. So this is the Merton setup. We're going to assume that the firm, if the firm falls below some barrier in the future, which is going to be the face value of debt, then it defaults. And that's going to happen at some fixed point in time t. Otherwise, it remains solvent. We're going to think about n firms, and the firms are going to have, the assets of the firms are going to be correlated. There's going to be correlated with the covariance matrix sigma. Okay, so in practice, we could probably just estimate the standard Merton model, right? So there is, in principle, solving n geometric Brownian motion is no more complicated than solving one. Except the issue is that in reality, if you wanted to do this in the data, you would have to know what sigma is. So you'd have to know not only what the volatility of each asset was, but you'd have to know what the correlation between each of those assets are. I.e., you'd have to know what every element of this matrix is. And there are n plus 1 over 2 elements in a matrix, independent elements in a matrix. Okay, so that is a large number, even for a small number of firms. So it becomes practically difficult to do this. So we will need a way of simplifying the problem, and we need a way of reducing the dimensionality of the problem. So we just have a small number of parameters to estimate. And in the simplest case, the Vazicek one-factor model is the following. What Vazicek does is that he assumes that there is a simple one-factor model driving all of the variation in the assets, where the one factor, we're going to call it Y, is going to be like a state of the economy factor. And so it's going to be a shock to GDP or a shock to productivity, etc. And everybody is going to have a sensitivity to that asset with a sensitivity equal to rho. So that's the rho is the correlation between the shock to the state of the economy and the value of the assets. Now, this is like the Cholesky decomposition, the way that we created in. So this is a Brownian motion. The sum of these two things is a Brownian motion. Right, because this here is an IID normal shock. This is an IID normal shock. Linear combinations of IID normal shocks are IID normal shocks. This still has the original properties of the Brownian motion, which we sketched out here yesterday. So this is going to be a one-factor model, and it's going to hold for all assets. So the correlation coefficient is going to ensure that when there is this shock that comes along to Y, all assets get exposed to it. And the question is, how does the correlation coefficient affect a CDO or a CLO, okay? Any multi-name product. Now, why is this going to be a tractable model? The critical point about this formulation is that conditional on observing Y, the state of the economy, all of the defaults will actually be independent. Because this is an IID shock independent for each asset. So that's the kind of trick in this model, is that everybody is exposed to a common factor plus an idiosyncratic shock. So the conditional on observing this bit, so this will make everybody correlated unconditionally. Exposure to this Y is going to make all of the firm assets move up and down, be correlated unconditionally. But conditionally on observing the Y, conditionally on knowing what GDP growth is, the only thing which is driving assets variation is the IID shock. Okay? So that's what's going to make the model tractable. It's going to be the difference between the unconditional correlation and the conditional correlation. Conditionally, on realizing a Y, the firm values and the defaults will be independent, and that's going to make everything very tractable. Okay? So, two more assumptions to make things, to remove the algebra but can easily be generalized. We just assume the default barrier for everybody is equal. So the face value of debt is the same for everybody. And the loss given default is the same for everyone. Okay. Okay, so this looks a lot like the mixed binomial model, okay? But it just has somewhat more of an economic intuition. What's the probability of observing D defaults? So we can invoke the law of iterated expectations or conditional expectations. The probability of observing exactly D defaults is going to be the following. It's the conditional probability of observing D defaults, conditional on observing Y, that is, integrated across all values of Y. Okay, so this is like an iterated expectations result where phi of Y is the density of Y. We integrate Y across all possible values, because this could be minus 20% GDP growth or plus 20% GDP growth, right? So it takes the real line. So this is the object that we want to compute. So actually I called it equation 1. Now what is the conditional probability? Well, this is just a binomial formula, right? So this is what I was talking about here. Conditional on observing Y, everything is independent. So conditional on observing Y, we have back to the binomial world. You see? This is the trick. In the binomial world, everything is independent. And so once we observe Y, well, what does Y do? Y is simply just going to change the probabilities, the mixing parameter. So here we're basically motivating a mixing parameter, okay, an economically motivated mixing parameter. So these are our two equations that we're going to put together. And the only thing that we need to do now is work out what is the distribution of Y. Well, what is going to be the distribution of Y? It's going to be normally distributed, right? So I chose it to be a normally distributed random variable. Okay, so we need to know that. Conditional on knowing that, we have independence. So let's just put this all together. The probability of... So the probability of default, conditional on Y, is the following. The probability of default conditional on Y is the probability that the value of the assets of each individual firm, okay, remember they're subject to an idiosyncratic shock, is less than the default barrier, conditional on observing some state of the economy. Okay, but the VI at capital T, okay, that is just like observing this value here, a common exposure to Y plus the idiosyncratic shock being less than Z. But what you can do is you can simply rearrange this in terms of epsilon. Everything else the only unknown in this line is the only uncertainty in this line is epsilon. Again, because this conditional expectation part, that means I know Y. So, rearrange it for the epsilon I. Rearrange it for the epsilon I, And then, of course, what does this mean? This is like Z being standardized almost. But epsilon I is normally distributed. It's IID. So what's the probability of observing an epsilon I small enough that we observe the fault? That's what this line says. Well, the probability of observing an epsilon I small enough, where small enough is just this quantity, is just the standard normal CDF with this argument. Okay? And then you're basically done. So, we know what this is. We know what this, actually, now we know what the PYs are. And if you put them all together, so if you plug this PY into this formula here, and then plug this formula into this formula, you get this line here. Okay, so let's just take a read of it. This is just these are just the PY, 1 minus PY. So these are the mixing parameters. Here's the binomial coefficients. And here's the binomial, so this is the binomial coefficient, and these are the binomial parameters. And this thing here, what is this? It's the standard normal CDF, standard normal PDF, integrated across all possible values of y. In practice, of course, you don't integrate things across plus or minus infinity, but you truncate things. So this is the probability of observing exactly D defaults. So then you can do things like, what is the probability of observing less than D defaults, where you just have to sum up each of these ends across, or you just have to introduce a summation. Right, so I would just compute D equals 1, D equals 2, D equals 3, D equals 4, all the way up to D equals n here. Okay, so this summation just gives me the CDF of the probability of observing 1 to 5 defaults. I'm just summing up this formula. Okay, so that's it, you're done. So this is like the economically motivated mixed binomial model. Okay, why does it work? Why is it analytical? Why does we can get a closed form solution here? Simply because of this observation that if I know y, conditional on observing y, the only difference between firms is a normal shock. However, how we evaluate that normal shock depends on the rho. So rho, the sensitivity of assets, sensitivity of the obliger's assets to this common factor is going to affect the probability of the number of defaults. And the question is, how does it affect the probability of the number of defaults? So let's look at another picture. So on the next slide, I'm showing you some plots where there is going to be there's going to be 100 assets in my portfolio. So this is going to be a CLO or a CDO with 100 assets with a single tranche. So it's just a basket CDS. And the individual probability of default is 5%. Okay, so this number, where are we? So under independence, the individual probability of default is going to be 5%. Okay, and we're just going to change the asset correlations. Okay, so I'm going to just increase the asset correlations, which is going to increase the exposure to this common factor. And this is what the thing looks like. So what I'm showing you here is the loss distribution for a one-period horizon. So there was 100 assets in my portfolio, and along the x-axis is the number of defaults, and along the y-axis is the probability of observing that number of defaults. So I'm plotting you this here, this object here. Okay, so the point here being, if we look at the independence case, when there is zero correlation, and there's zero correlation, what do we obtain? We obtain this normally distributed function around the mean. So this would be something you could just compute with the binomial model, okay, with as a p equals 5%. Now, what do we see as we increase the correlation? As we increase the correlation, as go from 0 to 50, we increase the number of, we increase two things. First, there is more chance that we observe a large number of defaults. Okay, there's more chance that we observe a large number of defaults, but unconditionally, not observing y, the probability of conditionally on observing y, there is the same probability of default for everyone. Conditionally on observing y, the same probability of default for everyone, which means that if we conditionally, what happens is as we increase the correlation, we increase the mass in this tail, but we increase the mass in this tail, the only way that we can increase the mass in this tail and keep the unconditional probability of default the same is if we also increase the mass in this tail. So that's the blue line. So I'm just showing you exactly the same thing. Again, we saw this in the binomial model. That when you increase default correlation, if it's the case that suddenly everybody defaults in recessions, but unconditionally the default probability is low, it means that we must increase the mass in both of the tails. And so this model would gives us, the moment we go to 5% probability, there is a quick decrease and a quick increase in the mass here. Just the parameters I've picked here, it didn't increase the mass too much here, but this is just I care more about the direction than the actual numbers here. Okay, so the takeaway here is that we can motivate the pricing of CDOs in a way which is consistent with Merton's model, and we end up getting the similar result that with a CDO, if we didn't know this, we would not understand the pricing of risks within the CDO. i.e. the equity tranche was probably less risky than we previously thought, and the senior tranche was probably more risky. Actually, that's exactly what we saw in the crisis, that the senior tranches actually defaulted much more than what people thought they would. Okay? So that's the point there. Okay, this model can be extended. So we can extend it in a number of ways. For example, we can introduce multiple shocks here. We can introduce individual sensitivities to the assets. So you can think about pricing a set of assets where you had a risky loans and safe loans. Risky loans would be one who had a larger sensitivity to risky loans were ones which had a larger sensitivity to the fundamental shock or the state of the economy shock. How do we do this? Well, you would just solve for the y in exactly the same. So how would you do it? So if every individual, if there was sectors, so I guess this should have an S here. So there is certain sectors of firms that have different exposures to the state of the economy. So for example, the pharmaceutical sector has a more, automotives are more pro-cyclical than pharmaceuticals, for example. They would have a different sensitivity here. How would you solve this model, extend this model to that? It would be simple. I mean, you would just solve for the conditional probability, the mixing parameter, subject to different sensitivities, and then you would just sum up these formulas, okay? Because conditional on observing y, then everything becomes independent. So this is a super tractable model. You can extend it in further different ways. You can have different state of the world parameters, and you could also introduce non-Gaussian shocks. Okay, one more thing then for today. So, in practice, this is not the formula that people use, because actually, if you take a look at this, it It's a closed form solution. Right, so I can compute this in closed form, except that it's a mess, right? There are many terms in here, and you can imagine if you have many, many assets, it could become quite hard to compute. So in general, it's messy. So fortunately, there is an extension to this formula called Vazicek's large portfolio approximation. So the Vazicek large portfolio approximation is the end of this 97 paper. So there's a reference for it. So the derivation I'm showing you here is from Schomburger's book, but it's kind of tough, and I've spelled it out here, but I just want to show you the main result. So it turns out that when you take this is a cumulative distribution function, right? Because I'm computing the probabilities over all possible realizations of default. It turns out that if that n, if the number of assets in my portfolio is very large, this, for the one-factor model, this messy formula, which has integrals for every single summation, right? So there is many, many things to compute here. The algebra is here. It becomes this animal here. Okay? And this is called Vazicek's large portfolio approximation. So you can see here, we have the same, so we have the same inputs. We have the row. So x is the number of defaults. Okay? So this is the density over x, which is the number of defaults. And it's just a simple exponential function. So this is a one line in MATLAB. Okay? So it doesn't essentially matter what is in this formula, apart from that you could even do this on Excel. The point of this exercise is to show you that with the large portfolio, so this portfolio approximation approach, if I have n equals 100, so what I'm showing you here is exactly the same result as above. So I have a general solution, which is the summation and the summation and the integrations. So these are the number of defaults again, and this is the probability of obtaining a particular number of defaults. So that's the probability of obtaining exactly 20 defaults. It was relatively low in the numbers that I picked. Here is I'm plotting you the general solution and the approximate solution. They're lying on top of each other. It shows you that for values of assets which are realistic for a product sold, a multi-name product, you don't need to go through the hassle of using the summation. You can just use the large portfolio approximation. If you go down to a smaller number of assets, it's actually not that bad either, right? Because if you take a look, okay, the distance between these two lines in basis points is not even that large. So anything above 30, so rule of thumb for this, you can use the Vazicek large portfolio approximation for anything above 30. And then you can just use this, you can price anything. Okay, that's it for today. So next week we have our summary class. So I sent out some practice questions last week. I will update those practice questions with the last 2 lectures. They're meant to be guidance for the type of question you'll see in the exam. Okay, so the exam, I promise you, will not be a surprise. And, I don't bell grades, so you can all get 100% as far as I care. Right? So the exam format is going to be the following. There's 5 questions. You answer all 5 questions. Okay, so the practice questions will be representative of the type of questions. They are essentially the past paper questions. Okay, and then I'll update them. What we'll do next week is I will go through the answers to those questions. If there are any particular other questions that you have, send me emails between now and at least Monday next week, and I will also answer those questions in class. So consult amongst yourselves what are the particular things, if any, that you would like me to focus on. Okay? Thanks.
There is a way of doing it. Your MATLAB will do it for you. It's more complicated. Actually, MATLAB is doing MATLAB is using popular to generate. So there's two things, right? So there's what we want to do, right? We want to generate these uniforms. And these uniforms are either coming from Gaussian. The two ways of generating a Gaussian sequence variable with a row of equal width, you generate what you could do. One application says take a Gaussian uncorrelated, so Z is 0, 1. Get the covariance matrix and do generate a Y good way to measure correlation if, for example, things come from T. A set of uniforms. U1 and U2. Right. Correlated. Are equal to. How are these numbers? Correlated, but yet not. Yeah? And here. Although they're positively correlated, they're going to go in this direction. It just means heavy tails means I'm more likely to draw. They're positive. I'm more likely to draw tails from the. Yeah, but this is exactly. So I'm more like if I draw a very small value. I'm more likely to draw very small values. Both of them, they will be heavily tailed here. If there was a if this was rho is equal to minus 0.80. It should still be a cloud, but there is like more mass here and more mass there. Yeah, so you can try this. So the alpha, the lower alpha has higher variance. Higher variance. But we know also part of the variance variance of the defaults. Binomial. This additional part is just the when the variance of p is 0, the variation. Binomial world. No, in the binomial world, but the other extreme. In that one, make the variance to be, I choose, well, that goes everybody default, probability 1, and that happens. Oh, or 1 minus b bar. If you just plug that into this number, this is obviously a world where there is large correlation between defaults. Either there's no default or everybody defaults. This is perfect correlation. Because it's either there's no default and they're perfectly correlated, or there's everybody defaults. This case is perfectly correlated. This here is perfect correlation. Yeah. So this is like saying bed larger than this. Say if I say of 1 minus p. However, if I maximize, and this is 0 correlation. Where there is maximum correlation. That tells you that variance and correlation are essentially the same. When I increase the variance, I also increase the correlation. For a fixed lower alpha, the variance goes up. Variance is higher and correlation. Correlation's higher, the variance is higher, and the only way that can happen is if I increases the mass of the I decrease equity, basically. I increase equity price and I decrease the.
But why, like, a lot of crime? I would take.
If I spread the distribution, there becomes a larger chance of a small number of defaults and a larger chance of a large number. In the very extreme case, if we go back to this is good. Oh, the probability of 0.9, so we're put to 1 minus p bar. probability of 1, everybody defaults, and that's the only time when the may increase correlation. Everything happens or nothing happens. Everything happens, very bad for senior. Then it gets ding ding ding. No, because for senior it was good. The only way that you can senior was not going to get the. Or for it to be bad for senior. Very bad. Be good. Yeah. Just need to make it a little bit less worse. It's very risky anyway. practice, what we're doing, so we're doing it, right, because generate to get out the margin. You pump it through a Gaussian, which gives you. It also says that you with this. Of uniforms. Back through to get this and this.
Yeah, this is more like already.
Generating a Gaussian coupler. Gaussian coupler is that you are generating related forces, forming them to uniforms. Generated uniform. Yes, that there is. Uniforms are put them in. Yeah, there's actually three, right? There's this. There's the two things. Any distribution you like. E, for example. A code was doing something like this. This, you pump it into the CDF, you get the uniforms. Back through the CDF. Marginals have the same. Yeah, that's the only thing you need. Yeah, you can do lots of things. Other code I gave you. I started Russians.